Hello and welcome to our presentation. Today we are going to talk about quantifying differences in expressive piano performances in the context of computational generative models. In the themes of RPPW, this fits into production. We talk about generative models of performance and computational perception of expressive performance. In this work, we focus on Western classical piano music, although some of these ideas might be relevant for other instruments and music traditions. This presentation will be structured as follows. First, I will present a small overview of computational models of expressive performance. Afterwards, I'll discuss some of the problems evaluating such models. Then, I will talk about some preliminary quantitative results and a small listening experiment. Finally, I will conclude the presentation discussing ongoing and future work. Computational models of expressive music performance can be used to generate an expressive, in this context we mean human-like performance of a piece given its score. For models of piano performance, these generated performances would typically include deviations in performance parameters such as tempo, timing, dynamics, and articulation. This is a generic framework for describing computational models of performance. The framework consists of three main elements: score features, which capture some of the information contained in the score; expressive parameters, which are numerical encodings of aspects of an expressive performance like timing and dynamics; and computational models, that is, mathematical functions or computer programs which relate them together. A central question with generative systems that produce some sort of artistic output is how to evaluate them. In the case of models of piano performance, earlier research focused on rule-based models, like Sundberg and Friberg's KTH model. In these models, when a new rule is proposed, a listening experiment is conducted to see if people agree with the rule. As you can imagine, this is very time-consuming and can get complicated whenever different rules start interacting with each other. Nowadays, there is a focus on data-driven or machine learning models, like the basis mixer or Virtuosonet from KAIST. To train such a model, real human performances are shown to the model, and the learning algorithm tries to minimize the reconstruction error between the predictions of the model and the human performances. A typical quantitative measure of reconstruction error are metrics derived from the Euclidean distance, such as the mean squared error. In this research, we focus on two main issues. First, these quantitative metrics of closeness do not necessarily imply perceptual nor musical or aesthetic closeness. Not all errors, that is, points or notes at which the generated performance is not identical to the human performance, would be perceived by listeners as equally important. For example, speeding up at the end of a phrase instead of slowing down might come as more unexpected or unmusical than simply playing the entire piece a little bit faster. Yet both cases might result in the same numerical distance. Second is the choice of reference human performances to compare the output of the model to. Pianists interpret music in different but musically equally valid ways. Here we introduce the concept of musical validity as independent of musical taste or aesthetic judgment. A listener might prefer a performance by Glenn Gould over another by Daniel Barenboim, but it should not be hard to argue that both of them are artistically valid ways to play music. Our ultimate goal would be a metric that can tell us if a performance is musically valid. We do not know whether such a metric exists, but we aim to use statistical machine learning models to approximate such a metric. In this way, we can both hopefully improve models of expressive performance, but more importantly, investigate how humans perceive and judge a performance. In this example, we have the first four bars of Mozart's A major sonata Köchel 331. Each of the curves below represent the tempo measured by beat period, that is, the duration of a beat in seconds. Each of the color lines represents an actual human performance from the Vienna 4x22 dataset. This dataset consists of 4 pieces performed by 22 pianists on a computer-controlled Bösendorfer grand piano, and the performances have been manually aligned to their scores. The thick black line is the average performance, and the gray areas represent a standard deviation from the average performance. We can see that most performances of this piece in the Vienna 4x22 dataset lie within this area. The thick red line is an artificially generated performance. that is a tempo curve consisting of random values within the distribution of tempo curves performed by the human pianists. We can see that if we pick one of the real performances as a reference, the distance between this reference and the artificially generated performance could be smaller than the distance between the other performances and the reference. Nevertheless, for a trained human listener, it would be very clear that such an artificially generated performance would not be musical. In this analysis, we take a broader view of this issue using two sets of tempo curves, 22 coming from performances of a Schubert dance in the Vienna 4x22 dataset, and 22 artificially generated performances of the same piece, as described in the above Mozart example. In this plot, each dot represents a tempo curve, in blue the human performances and in orange the artificially generated ones. We computed the pairwise distances between all curves with different metrics, the L1 norm, the Euclidean, the cosine, and a learned metric. We use multidimensional scaling to project the data on a 2D plane that respects the high-dimensional distances. The amount of randomization was chosen such that under mean-squared error, a human performance is closer to a human reference in 50% of the cases in the top row and 90% of the cases in the bottom row. Generally, the more randomization is added, the 90% case, the clearer becomes the clustering. In this plot, it is clear that if we pick a human performance as a reference, there are artificially generated performances that are at similar distance than the closest human performances, while other real human performances are even more distant, or less similar according to these metrics. We can see that some of the metrics are slightly better at clustering together human performances, but the separation of human and artificially generated performances is still not perfect. Previously, we noted our intuition that listeners are able to discern artificially generated performances from human performances more reliably than common distance metrics. To address this question, we devised a listening test. The test consists of 16 forced-choice questions. In each of these questions, we present a human and an artificially generated performance of the same piece, and listeners are asked to identify which one is the human performance. The artificially generated performances were constructed such that only one expressive parameter was randomly generated: dynamics, timing, tempo, or articulation, while the others, including pedaling, remained the same. This randomization was generated in the two noise levels described previously, 50 and 90%, as in the multidimensional scaling example above. In the table, we report the percentage of questions where listeners correctly identify the human performance. The cases where the difference is statistically significant are highlighted in red. For tempo and articulation, listeners were able to identify human performances even when mean-squared error-based evaluation failed. Dynamics and timing were more complicated. This might have to do with how dynamics were modeled, with MIDI velocity, and the complex effects of timing, like melody lead and melody lag. Fine-grained analysis is ongoing, but these results illustrate the need for improved perceptually informed metrics that take into account musical structure. We expect the results to show the limitation of standard measures of similarity between performances and serve as a basis for discussing implications for quantitative evaluation of generative models of performance. Furthermore, we aim to derive recommendations for the evaluation of computational models. Future work will include investigating the contribution and interaction of different performance parameters, like tempo, dynamics, and articulation, to the perception of similarity in performances. Thank you for your attention.